number line in green because it's real, like greenery. Okay. And my imaginary line, say blue, like the sky going up. There is actually a different suggestion for this line. These numbers, instead of calling imaginary numbers, we can call them, this is not my creation, I read it somewhere, lateral numbers. Lateral, right? That I like it. Real numbers and lateral numbers, because they are lateral. They are living this way, perpendicular. Right. So now this is your real number line. Now this looks like an XY coordinate plane that we use to draw graphs, but this is not that. This is the plane where our numbers live in. I'm just drawing that plane. So this green line is our familiar real number line. And this blue line is the new line that we created, which is perpendicular and passing through 0, 0, 0 on the real line. It's perpendicular to that, and it's going through the 0 on the real line. And we actually like put it like an axis here, and we write real here, just to say that's a real number line. And then for the imaginary one, so this line is the imaginary number line. Right? So we just say that's the imaginary line or imaginary axis. In short, we use the little shortened form im and re for this. We write re only for that sometimes. And for the imaginary axis, the way they call it, we say im. And on this line, we have all the real numbers live on here, live on this, and all the square roots of negative numbers live on this, and they are what are called imaginary, right? Numbers live on this. And so on the imaginary, on the real line, this is nothing new. We have 0, 1, and why does it happen? 1, 2, 3. So it's an infinitely long line, and you have minus 3 and so on. All the rationals, fractions, all those are here. And then on the imaginary line, you have the number that has a length of 1 is the square root of -1. So it's the square root of -1, and we give it this symbol I. Originally, it was a Greek letter called iota. It goes like that, iota, but now we use I because it's easier. Okay, that's no big deal. And then, so we label numbers in terms of I, that this is for convenience. It's difficult to always say square root of -1, square root of -1, because any other square root of any other negative number could be written as a multiple of I times something, I times a real little part. Did someone say miss?
Yes, miss. Sorry, are we supposed to draw this?
No. I'm just bringing everything together and like giving you the final picture, and then we have a little bit to write. I want to start writing too. Don't draw this. Okay. So all square root of any negative number can be written as a multiple of I, that is a multiple of square root of -1. You think about what I just said. So if this is I, then after a distance of exactly the same amount, just like on the real number line, you have in units of 1, you have 1, 2, 3 going on. Here you have 2i here, and then 3i here. But what does 2i mean? 2i is square root of -4. 3i is square root of -9, and so on. And in between you have all, so on this, you just think about it, okay? Just take a number, take the square root of some any negative number you want and see whether you can find a place. It will be on this line. Okay. And then you have negative I, negative 2i, negative 3i, and so on. Okay. So we don't, we actually, so we have to adapt to this use of I. So I is just square root of negative 1. So something important to remember is, what is I squared?
Minus 1.
You will say it mechanically.
Minus 1.
Minus 1, because, yeah, right? Because I is the symbol given to square root of negative 1. So then I times I is what minus 1 is. So we will write all that later. We will write all that later. So I'm just giving you the picture now again. And then any number somewhere, say here, say you have, think of a number right here. Why does that happen? Think of a number here. Okay. What is that number? That number is, now the way we read this is similar to how we read coordinates in XY plane. And that should make sense to you. What is this number? It has a component, a real component, the vanilla part of 2.
2 plus I.
And it also has, yeah, a little bit of imaginary part. That, so we write it as plus I. It's a sum of a real part and an imaginary part. Okay, so if you think of any point here, would have a completely pure real part and an imaginary part. So we generalize this and say, any point on this whole plane, be it a point even on the line, could be written in the form A plus BI, where A is the vanilla component, B is the chocolate component. A is the real component of that number, and B, that amount of I. B is the imaginary component. So even a number like minus 2, if you take this number, it's pure real, but it's a complex number. It's minus 2 plus 0i. No chocolate component, 0i. If you think of a point on the imaginary line, a number on the imaginary line, that minus I is also a complex number. That is 0 plus minus I, minus 1i. So any number could be written in this form, A plus BI. You can think of it as having, so that this number has no real part. 0 is the real part. Okay. So any point on this line, we say has this form. So we'll come, that is where we start the formalization of all this. I hope you have the big picture now. Let's start writing. So I'm going to give you a little bit of a note here. Usually, I don't give lengthy notes like in other, like it's not like a history lesson, but for this, I'm going to give you a little note. You will have some writing to do. And I hope it's okay with you. Sorry, I'm just now only seeing what you have asked here. Because while I write, I can't see your chat box. I have to press it and get it. Let's start writing now. So bear in mind everything that you heard today in this lesson, and we will write it. Everything that I explained won't go into the note, but I hope you will remember all that. Right, let's start writing, okay? I'm just going to dictate. Is that okay? Or, actually, do you know how to save this? I'm not sure how to save it. If I take a new page, would this go away? Are they all here? Are they all here?
Yes.
Do you see this one, no? Today's one? This one, no? Edited 822. So it will be there, no? It will be there. Okay, I'll take a new one. Okay. I'll write with you. I think, oops. I dragged this. Hope I didn't scratch it. Okay. Now let's write. I will dictate and I will write too. The number system that we know up to now I'm going to minimize this. The number system that we know up to now is the, can't write there, no? Oops. Is the real number line in red. And I'm using capital letters. Real number line. All the different types of numbers are situated on this line. And then you draw a line. Natural numbers. I will just label some of the numbers on this. The 0. We have all the numbers. And let's show a few fractions. They're everywhere. I'm just showing some examples, right? Fractions are the in-between numbers. And there are numbers like pi or √2. And let's mark some important ones. There is E somewhere here. There is E. There is √2 would be like 1 point somewhere here. √2. Just remember that there are more irrationals than all the rationals on this line, which is in itself is mind-blowing to me, because we only talk about those numbers very rarely, and we only talk about only a few of them. Always it's √2, E, and pi. There are so many that because we can't write them down, we don't use. I mean, we don't talk about them.
So it's basically any number between any two integer numbers are irrational numbers, right?
No.
Not every except for the fractions. Except for the
No, say it
proper
again.
fractions. So except for the proper fractions, if you take between two integers, the rest of it is just irrational numbers, right?
That's correct. That's correct. Between, I mean, take any two numbers, this and this, take these two, right? Take this and this. Now there are numbers in between, there are numbers here. Take off all the fractional numbers there. The rest are irrational. Is that what you said? And there are more irrational numbers than the rational numbers there.
Yeah, that's what I was trying.
Okay. Okay. Hope you have finished drawing with me. So I will go up.
Oh, Miss, can you give me a second?
Okay.
Go back the whole thing. I want to see the whole point again. Oh, okay, Miss. Okay.
Okay, then let's write. All these types of numbers, all these types of numbers make up the real numbers. Every real number is represented by a unique point on this line. And vice versa. That means every real number is represented by a unique point on this line, and every point represents a unique real number. New paragraph. For a very long time, mathematicians avoided expressions such as square root of negative, say, negative 12, put any number. That is square roots of, oops, I'll write that in a different color. That is square roots of negative numbers. There was.
Miss, why did mathematicians need to know the negative square root? Like for what applications?
Say that again. For what?
Why did they want to know the negative square root? Like, were there any applications which needed?
Yeah, good question. So it first came up just like, let me show my thumbnail again. It first came up in solving equations. That's where it came up. So they created it to bring something for a solution to that. Now, just like how they created negative numbers when they had x plus 5 equals 3, the example I took earlier. So this is 3 take away 5, and in order to have a solution here, no, let's stop saying that there is no solution, that this doesn't exist. Let's bring that number 3 minus 5, that number is minus 2. So they created it just like that as a way of being able to solve this kind of an equation. When you end up, if you end up x squared is equal to a negative number, then x would be equal to the square root of that negative number, and we would be stuck there and we would say it doesn't exist. Just so that we can talk about a solution there, they brought it in, but later they found applications of this. I'm not very familiar with that, but if you do in physics, in electricity, AC and DC currents like it's happening like that, and complex numbers are used to work, like do calculations related to that. So there are applications, just like what are the applications of negative numbers? When you want to talk about debt, or when you want to talk about something moving in an opposite direction, you use negative. Just like that, later they found applications of these imaginary numbers.
For like vector quantities, we need negative values.
Exactly. Any vector physical quantity, you need negative numbers to indicate the direction. And there are applications of imaginary numbers from what I know, in electricity. In electricity, there are more. The thing is this: so I have not learned those stuff, but there are applications there. There are applications of real life applications of complex numbers, imaginary numbers, and it's difficult to imagine that there could be an application of this. Where would we need this? There are. It's because it's new to us. We don't see it, and until you learn such an application, you wouldn't know it. But I know that there is in electricity. Theory of electricity, there is. What did we say? There was no number. There was no number on the real number line that when multiplied by itself, would give a negative number. So they were non-existent. So
Miss, can you scroll it upwards a little bit?
Yep. Enough.
Okay.
So they were non-existent. But it was only until humans were creative enough. I'm going to use the word creative, or brave enough, or creative enough to expand our number system. From, I'm going to use a different color, from one dimension, from 1D, from a 1D line, one-dimensional line is the word here, from 1D line to a 2D plane. To fill this impossible, not fill, to fit these impossible, these impossible creatures in. So they were non-existent, but it was only until humans were creative enough to expand our number system from a 1D line to a 2D plane, from a 1D line to a 2D plane to fit these impossible creatures in. New paragraph. Then they were no longer non-existent. They were no longer.
Miss, can you scroll up for a second?
Yes, sure.
Miss,
Yeah, Tarindu?
Miss, now we drew this on an axis telling that the real number system is on the horizontal axis and the imaginary ones are in the vertical thing.
Yeah, yeah.
So, Miss, are they vectors?
Are they?
Vectors?
Are they what?
Vectors, do they have a direction?
Are they vectors? So I mean, vectors is another model. Yeah, numbers can be thought of as vectors. Actually, it's useful to think of a number as a vector. Now, in my multiplication little model,
Miss, but then
look,
before the before the imaginary plane came up,
yeah,
weren't they vectors anyway? Since they were going like backwards to the negative direction.
vectors were there.
Yeah, like it's not that the complex plane created changed it to a vector, right? It was already
No,
a vector.
no.
Oh, okay.
I'm not sure what you are like. The vectors knowledge we already had.
Yeah. Okay. I understand.
The vectors is a model. All these are models actually. And yeah, and now we are used to thinking of a number as a point. A point. Even if you are thinking only of the real number line, we think of a number on the line as a point on the line. A better way of thinking of a number is as a vector starting from 0, as a position vector. Thinking in terms of vectors is a very useful way of thinking. Actually, I think we might, yeah, if you can get used to that way of thinking of a number as a vector, it's very useful. Because the thing is, then you see the size of it. When it is a point, you are just seeing the location where the number is. But when you draw the vector, you know how large, any number has a size here. It has a magnitude. So when we draw the vector, like you see the size, you see where it is. When it's just a point, I don't know whether you see that, the difference. Okay, so let's continue this. Then they were no longer non-existent. Oh. All square roots of all negative numbers. Oh, wait. Okay. Which way sounds better? All square roots of negative numbers or square roots of all negative numbers?
What? Miss, can you repeat again?
Square roots of all, right? Yeah. Which sounds better? I asked. All square roots of negative numbers or square roots of all negative numbers? Square roots of all negative numbers. That's what I want to say. Yeah. Then they were no longer non-existent. Square roots of, okay, let me write that in blue. Square roots of all negative numbers could be thought of as existing on a I'm writing in a different color, on a perpendicular line to the real line. With that multiplication model, I was explaining why we came up with a perpendicular line. Okay, I mean, even without that knowledge, you will do this topic well. I mean, what we are actually the whole lesson today. Now it's only 8:45. All the 3 hours I just spent to give you this different picture of this whole lesson. I didn't go into any details yet, right? No computations. We didn't even start anything. But I think that this is important. I think this is what is important.
Yeah, I felt like I
Right.
needed this.
And the rest will build very quickly then, because you have this nice foundation.
Now it just kind of makes sense.
Yes, everything will quickly make sense to you. We can do the rest very fast now.
Now I see the world in a different angle.
Existing on a perpendicular line to the real line. These numbers were called impossible or imaginary. Impossible in red. Impossible. There is nothing impossible about it. They are very possible, but impossible or imaginary numbers. Okay. And then you draw this new, we use green for this. And we use blue. Come on, 90, okay. I'm saying imaginary line, real line, 0, and you have your 1, 2, 3, 4 here, and so on. -1, -2, -3, -4, and so on there. And here you have square root of -1. And equally spaced, you have next one is square root of -4. Equally spaced, you have square root of -9, and so on. I still didn't bring in the notation I. I will bring that in the next one. The negative square root of negative. Okay. Difficult to say also. Negative square root of -4. Negative square root of -9, and so on. You see, this number is actually and this might be another thing to like. I'm looking for a color. Okay, wait. I need a color. Like this number is twice as large as this number. Magnitude wise, do you see that? Look at the placement now. These spaces are the same. This space, that's 1 unit. This the length 1, and this is also length is 1. So the magnitude of I is 1, and magnitude of square root of -4 is 2. It's in size. It's too long. Don't add those little things that I added to this, okay? I just wanted to point that out here. Oops. I'm moving this up. I hope it's okay. Later, Euler. Heard of Euler? Oops. Oh, you have been saying things. Wait. Oh wow, I didn't see any of this. which means the matrix is real. Seriously, though my whole perspective has changed. Why the matrix? Tarindu is the one to always get you to, guys, focus. When you like deviate into a movie theme or something, Nathan, excuse me, you're telling me to focus. Don't get me started. She'll then write the, exactly. She'll then write the note. Okay. I'm sorry, I'm missing out on all the fun that you're having on the chat because when I write, I can't see what's going on there. Okay, what you're saying now. Wait, aren't we supposed to draw the diagram? Yes, you are supposed to draw the diagram. Did you not?
I was drawing it halfway through and then.
Okay,
Wait,
so just
Miss, can you scroll it up for a second? I'll take a screenshot and then draw it later.
It's just, I mean, just have a look. You can take a snapshot in your mind of this. It's easy diagram.
Yeah, okay, got it. It's in my mind.
Right. Okay. Then later, Euler introduced the symbol I to denote square root of -1. And now we have a convenient way of what? Way of writing it. Wait, so way of writing it. I is called the imaginary unit. The word unit means it's 1 unit long. It's on the imaginary line. It's like if you want to go in 1 unit measurements, I is the one. It's like 1 on the real axis. It's I on the imaginary axis, right? It's the imaginary unit. It's 1 unit long. It's imaginary. Oh, it's not J, it's G. Imaginary unit. And let's just write this also. So I squared is 1. Do you see that? On a side, I'll write that what have I written here? Square root of -1 times square root of -1 is -1. Okay. This is just my side bubble. And then write, and with this, and with this creation, it's all, everything in math, it's all created. And with this creation, it gave rise of the planet of the apes. No, that's not what it is. Rise of the apes, whatever. It gave rise to a a whole
Yes, I can see what's after square root -1.
You can't see? What?
I can't see in that point what's after square root and
Okay.
Okay. No, that sign out thing.
Here, my thumbnail is blocking. Yeah, okay.
Yeah.
Miss, the red box isn't supposed to be -1.
Oh, it is. Oop, not black. Right. See now? That's how easily a little thing can happen. You see, everything would be wrong now if you wrote like that. Ayyo. I squared is -1. I have written it here in the side bubble. Side bubble. Yes, thank you. Yeah, you see, and you know, especially me, you know, I mix up words. I say left when I want to say right. Please watch out for these things, okay? You will be writing the wrong thing in your note. Oh my God. Right, okay, anyway. So, and with this, and with this creation, it gave rise to a whole, I was just singing also, you didn't hear me singing, you know, the whole new, not the whole new word, the whole new, what? Kind of numbers, the whole new, oops. I meant to write in this color, the whole new. Kind of numbers. Since now, come on. Since now, there can be numbers. There can be numbers anywhere on this plane. There can be numbers anywhere on this. I want to write plane in a different color. It's a plane now. It's no more a line. It's a freaking plane now. And all these numbers, all these numbers on this plane is what we call complex numbers. All these numbers on this plane are called in red complex numbers. If you want, you can write in brackets, which is a bad choice of word for this kind of numbers. And in singular, we say Sankirna Sankhya. Sankirna, my goodness. There's nothing Sankirna about them, but. And you know what? Wait. And in brackets, you know the symbol we use for now, usually in algebra, for an unknown number, usually the numbers were real numbers too. So when you have an unknown number, you would say X. Now you know what letter we use? Z. Like if you want to refer to an unknown number and you are thinking of numbers in the full sense that your number could be even a any number, not just real, complex number, you would say Z. Then that gives an indication, oh, you're talking about the whole plane, right? You know, like that. So Z is used. Z is used as the symbol for a complex number. Okay. So these numbers consist of a real part. I'll come to that separately later. I'm just putting it in the note here. Real part and imaginary part. Are you keeping up with me, or like I'm going to draw? Okay, and then a little bit more, and then we are going into the. So a number on the real line. Let me put that in. a number on the real line would be pure real, pure vanilla. No contamination of imaginary, like pure real, right? Will be pure real with no imaginary component, with no imaginary component, and a number, what was my color? Blue, no? Number on the imaginary line, a number on the imaginary line would be your imaginary. With no real part. With no real component.
Miss, can you take it up for a second?
Yeah, sure. Enough.
Okay, Miss.
La, 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 la. I'm just going to like now only I'm showing you this is I, it's 2I, 3I, that's how it goes, right? Minus I, minus 2I, minus 3I. If you want to see now in the earlier diagram, I had written 2I as square root of -4. If you want to see how it became 2I, you can actually show in a little bubble. Square root of -4 can be written as square root of -1 times 4. You can break it down to -4, and that is I, and this is 2, and that is 2I. That's if you want, okay? 1, 2, 3, 4. 1, 2, 3. So pure real imaginary, and in between you
Miss,
have.
what did I miss? I got disconnected.
Oh, I don't know how long you were disconnected.
I think for 30 seconds maybe.
Then not much. I'm sure you just have to draw this.
Okay. No, I didn't.
Have you written this? Have you written
Pure,
this?
wait, hold on. Pure imaginary with no real component. Okay. I'll just draw that. Okay. That's it.
And any number in between, like say, if I call this one, this would be 1 plus I. I will get to that in the next subtopic, but I will write this number right here. Now, here's another thing. This is a number, one number. 1 plus I is a number. It will take some getting used to. It looks like an expression with the sum of two things. It is a sum of it. It just shows the two flavors, but it's one number. So you can show like So this is a complex, it's a mixed. These are my words, okay? They are not. It's a mixed, and all these are what complex numbers are. Let's say mix of both. A mix of both. So any number like on these quadrants, not on a line, but on the space in the quadrants, they have a mix. Okay, we have to stop. We've gone past. This is a good place to stop. And next week, we are getting into the terminology and addition, subtraction, all the computational stuff with imaginary numbers and the notations and all the formalities. Okay. Let me zoom this in a little bit so that you can. Let me know when you are done copying so that I can go back to the. Hello.
Done.
Anit line.
Miss, I'm done.
Done, huh? Okay. Okay, so I'm going to change the screen, go back to this. So we are done for the day. Please keep thinking about all of what we saw today and look forward to what's coming next. Everything else is as interesting. The computer, now it gets more interesting now, okay? Right, I will not spend any more time. Let me know if anyone needs a recording. Have a good.
Miss, can you send me yesterday's recording?
Yesterday's?
Yeah.
The revision. And
Miss, can
one
I
more-
also have it?
Yeah, can you drop